How's that?
Yes, we start now. All right, so it's a great pleasure to have Professor Xiaoqi Yang giving a talk today in our variational analysis series. And it's a great pleasure also for me to introduce him. He's actually one of the earliest research connections that I have, because I met him when I was doing my PhD in Hong Kong at Hong Kong Polytechnic University. And I have hugely benefited from the environment, right, from the research environment, because Xiaoqi also has a lot of students and visitors, and was just a great thing to experience and meet a lot of people there. And I guess he doesn't need much introduction, because I think a lot of people here are either aware of his work, right, through reading papers and journals, or met him in person or collaborated with him. But nevertheless, I'm just going to give a quick overview. So Professor Yan received his bachelor's degree from Chongqing University in Chongqing, and then master's degree in operations research and control theory from Institute of System Science at Chinese Academy of Sciences in Beijing. And then he got his PhD from University of New South Wales, and then worked in Australia for 5 years at the University of Western Australia. So I'm actually wondering how many people here met Xiaoqi in Australia, not in Hong Kong, right? From a while ago. I wonder how many Australians already were here in Australia when he was doing his PhD and working here. And then he moved to Hong Kong and became full professor at Hong Kong Polytechnic University in 2005. And also, I would like to mention that Professor Yan received a lot of awards, amongst them the ISI Citation Classic for his paper in Journal of Mathematical Analysis and Applications. He received the first prize of natural science from the Chongqing municipal government. And also twice he has received President's Award for Outstanding Performance from Hong Kong Polytechnic University. And of course, we are all aware of his scientific contribution, and we have enjoyed his research papers and research discussions and so on. So it's a great pleasure to have you here today giving a talk. So please go ahead.
Thank you, Vera, for your very kind introduction. It's my pleasure to give my talk here. Yeah, I was in Australia years ago. I'd love to work there. Hope someday I'll go back. Today I'll talk about the error bounds modulus for locally Lipschitz and the regular functions. In particular, probably emphasize on the far and near end sets. So this is joint work with Minghua and Kevin. So outline here, I'll talk first about the definition, far and near ends of a closed convex set. Then the part 2 is when these sets are closed. Then part 3, I'll talk about the local error bound modulus. Finally, a brief conclusion. Okay, start from the definition. For a convex set, closed convex set C and the point x0, now we can define the far end and the near end. So the far end of C relative to x0 is all the points x in C, where we have the x0 plus t times x minus x0 does not belong to C if t is greater than 1. So if t is equal to 1, then this combination here is just equal to x. So that's in C here. But as long as t is go beyond 1, then this combination is not in C anymore. So let's say something, we have all this kind of boundary point of the C, but this is t here is greater than 1. So this far ends of C relative to x is those part of boundary of the C if you're looking from the x0, which is far end part. I think geometrically the definition is very clear. You're just looking from the, doesn't matter, X is C is a convex set. And you're looking from the x0 point. then you say which part of the far boundary of the C. So that's the far end of C. Then another part we can say is the near end of C relative to x0. So there are two cases here. If x0 is not in C, then we still can see the set C. Then the near part of the boundary of the C, we're looking for the x0. So those parts, the near part of the boundary, you're looking for the x0. So that's the near end of C relative to x0. In another case, if x0 is not inside the C, then we just simply define this near end is equal to x0. So that's two concepts here I started with. So one is the far end, one is the near end. So the definition was first defined by the, I think, Professor Hu in North Illinois, who defined this far end of C relative to 0, the orange. Then I'll start with some property here. Now for the far end of C, we can summarize some basic properties here. The item 1, item A here. So if the far end of C is identically equal to C, if for all the x0 is not in the affine space of C. So this is true. So if you're looking at the C convex set is one 9 segment, just one 9 segment in the space. If you're standing R0, x0 on one side of this 9 segment, so x0 is not in the affine space. So in that case, you're looking at from the x0, so if the farthest boundary is simply, it is identical to the C as well. So in this case, the far end is equal to C. Then item B here, so the far end of C intersects the relative interior of C is equal to empty. For the case if X is inside X, or either the x0 is in the affine space, but not in the C. So that's if C is inside, if x0 is inside the C, so in that case, you'll say the boundary is around, but the interior is inside. So in that case, these two sets have no intersection. Now for the part C, this far end is not equal to empty. It's not empty as long as the poles of C minus x0 minus the horizon cone of C. So this condition here is something like you cannot have a C in all the direction is bounded. So you must have some part of C here, which the boundary is bounded. So in this part of boundary here, so that does not belong to the horizon direction. So in this case, now we have the far end of C is not equal to empty. So the far end does not go to infinity. So that's for the far end of C. For the near end, we can have similar result, but I do not present it here. Then for another result here, I need to use another concept is called the shadow of C relative to x0. So shadow is the union of all the half line like this one here, where the x is equal to, where x is in C. So that's you're just looking from the x0. So all the shadow, all the part you cannot see, which is shadowed by C. So that's called the shadow. So we have this lemma here, which gives us two results on the far end and the near end. So for the far end, so if we have for the far end, that means we can extend the C here. The far end of C is equal to the far end of this closure here. The closure, as you can see here, the closure here is the closure of the convex hull of C union X0. So in that case, if you include the X0 inside the C you are considering, then this does not change the far end of C. Then on the another result for the near end of C here. So nearest end of C, because we are looking from the X0, the near part of the boundary of the C, then if you extend the C here to the shadow of the C, shadow is on the other side of the C. So in that case, this shadow of C relative to X0 and the original C, they have the same near ends. So these are the two set of the basic property here. Now I'm going to establish some geometric structure about how do we describe the far end. All right, so in this case, I did some concepts from the convex analysis. One is the concept is the face. So a face of the C, so it's those kind of subset C prime. So in that case, if you have any closed line segment in C, but with the interior point is in C prime, then in that case, those two endpoints of the line segment must be again in this C prime. So this is well known concept. Another one here is exposed face of the C. So this again, it is a face first. Then this face here is also the intersection of the C and supporting hyperplane to the C. Right. So this is one part of the face. Now I also did the concept of the support function. So support function of the convex set C, the sigma C is defined as supremum of this inner product of X and W, and the W here is inside the C. All right, so that's the support. Now we can calculate the support function. So its subdifferential is equal to the argmax of this inner product over the C is in over the V in C. So this argmax is basically can be calculated is equal to C intersect this hyperplane. Right. Now we say for exposed face, when a face is an exposed face, so F is an exposed face of the C, if and only if F is equal to this subdifferential of the support function. As we can see from the line above, the subdifferential is the intersection of the C and this hyperplane. But in general, this hyperplane might not be supporting hyperplane. So in general, this subdifferential might not be the exposed face, but it is exposed face. Now we need to have the condition here, the W is not equal to 0. So if this is true, W is not equal to 0, then this hyperplane become a supporting hyperplane for the C. Now in that case, this subdifferential of the support function is exposed face of the C. Now we give some structure about the far end set. For the set C here, now we first consider the X0 here is inside the C. So in this case, we have two results here. The first one is the far end of C relative to X0 consists of all the faces of C such that X0 is not in that face. So if you're looking at, in particular, you can look at the polyhedral case. If you have this X0 is in one of the faces, if x0 is in one of the faces, then in that case, of course, this face, even though it is might be one face, but this face wouldn't be in far end of this set C, because if you're standing on this face, of course it is not. Then in this case here now remember now we have x0 is inside the C. So in this case now we have the result B here. So we say that the set consisting of all the exposed faces F of C such that x0 is not in F is a dense subset of the far end. So consisting of all the exposed face, that basically is we put all the union, all these faces together, this union here, in case we have the sigma C at W is greater than this inner product. In this case here, this one condition guarantee this is support face, exposed face. So this union basically is the exposed face F of all of the C of the C to C, right? So this union is included in the far end of C. Then again, this set here is included the closure of the union. So in that way, we say that the far end of C or the union is dense in this far end. Right. So this case here, so the case is some corner point. So if you're looking at if why it is we do not have equal. This is the reason we do not have equal is some kind of corner point. Probably one side is flat, one side is has curvature. So those kind of face which is not exposed face, but it is possibly is in the far end, right? So those are excluded. So we can have this this union here is a dense set in this far end. So similarly, if x0 is not in C, then we can still have similar results. For the near end, now we have only one result here. So that we're considering the x0 is not in C, because x0, if it's in the C, now we have only 1 point for the near end. So we will use this C prime here. So C prime, we take C prime is the shadow of C relative to x0. So the first result here, so again, what is the near end? So near end consists of all the common faces of the C and the C prime such that x0 is not in the affine space of F. Right. So you're looking at the C and the C prime. So C is a convex set. Now C prime is the shadow of C. Right. So what is the common face? So common faces is a part of the faces or part of the boundary which is near x0. So that's the near end. So we have a common faces of C and its shadow. So those basically give us the near end. Then again, similarly, now all these common faces or common exposed face, you put them together are this union. So in this case, now we have, because now we're talking about near, so this support function value is less than or equal to this inner product. So in this way, this union is include the near end, then which is include the closure. So again, the union is dense is the near end. So that's the result here, the basic result of a far and near end results. Then I connect some literature here, very few literature, then how I'm going to use this far end to do analysis, to do this variational analysis. So basically 2005, Professor Hu showed for convex inequality, f of x is less than 0, for which that its strong BCQ is equal to BCQ plus the distance from 0 to this far end of the subdifferential of f relative to 0. This distance is equal to 0. So strong BCQ is stronger than BCQ. So they are equivalent. If we have an additional assumption, this distance here is positive. So this, I think, is a very important application of the far end set. So of course, I do not explain what is BCQ, what is the strong BCQ. Right. Then in 2007, who studied the global error bound for the level set of a convex function by a weak BCQ. Again, plus another condition here, which is distance from 0 to the far end of the subdifferential intersect the normal cone. Again, they use this distance here. So actually, Kyle and Vera, we studied the exact tangent approximation of a convex set. So when this exact tangent approximation holds, so I'll come back to this concept later. I'll use it later on. Then also about the relative continuity of the gauge function. So these two are equivalent. The equivalence of these two concepts here is true by the equivalence of that error bound of a support function and this condition here. So that says that if the global error bound of a support function is equivalent to this distance is positive, then there's three conditions here, three parts here that they are all equivalent. So here I will also use the far end of C. Then another reference here by Zheng and N, 2004, they used this concept in one of the in the proof of one of the results, but they didn't explicitly mention about this far end concept. So again, they use this positive distance to show that the kind of the metric subregularity of the solution set of a generalized equation, that's 0 belongs to the set value mapping, is equivalent to the strong BCQ. All right, so that's give some brief account about the application of the far end. All right, so this is the first part of my talk here. Then I'll come to say when for this far end and the near end, when they are closed. So it is a boundary of the convex set. So how can we characterize this set? The closeness of this set. Right. So I'll use the concept about the gauge function and the cogauge function. So in the case for the 0 is inside the C, now we can define the gauge function, the gamma C, by the information of all the non-negative lambda such that x belongs to lambda C. All right, so in this case, we have a point anywhere where the x is. Now, if x belongs to this lambda C, then possibly you have many lambda, but you just choose the smallest one. Now, this function can be shown it is lower semi-continuous and sublinear. Its domain is equivalent. Its domain is equal to the post C. So that's a gauge function. For the case that x0 is not in C, we can define the cogauge function, Lucy. So Lucy here is defined as supremum of all the non-negative lambda such that such that x belongs to lambda C. So here we take the limit sup. So we take the here we take the supremum So in this case, if somehow if C is not bounded, so this one might likely is equal to plus infinity. So in this case, we can show it is upper semi-continuous and is superlinear. So now we can say, as I mentioned, this might be blew out. So we can say the domain of the negative root C. So it's hard, I think, we don't talk about domain of the negative root C is equal to the closure of the post C. We do not talk about directly the domain of C, because that case is probably not related to C anymore. So idea to have the gauge function and the cogauge function to carry out. So then we notice a fact that for a sublinear function, if it is continuous at 0, then this function, the whole function, the function is continuous everywhere. So that's the property, nice property for a sublinear function defined on the whole space. But if a sublinear function not defined on the whole space, this property might not be true. So if we look at this function P, if x is equal to 0 on this line, now we have an absolute value of y. If x is positive, now we have flat 0. So in this case, now the P is only defined on the half space, x is greater than 0. Now we can show the P is continuous at the range relative to this half space, its domain. But this function is not continuous relative to this half space anywhere else on this line, say x is equal to 0. So on x equal to 0, only continuous at the 0 points. Anywhere else, it is not. So this is a case that which for sublinear function not defined on the whole space, so we might not have different feature here. All right, then we have the first result about the continuity of the gauge function. So we have a C, again, 0 is not in, 0 is in C. Then we have this two condition, we have this two, oh, sorry, this equivalent is not true. We have this two conclusion here, no, this equivalent. All right, the first one here, the gauge function is continuous at 0 relative to its domain if only if this distance from 0 to the far end of C is positive. So we give a characterization of the continuity of the gauge function at 0 points. As long as this distance is positive, then this function is continuous at 0. Then the second result here, we're talking about the gauge function is continuous anywhere on its domain. So we're talking about continuity on the whole domain relative to the domain, of course, itself. If and only if this far end set itself is closed. So that's two results about the continuity of the gauge function. So in the same way, we can talk about the continuity of the cogauge function. So the cogauge function, now we say that the x0 is not in C, plus that C satisfies that the lambda times C is in C for all the lambda is greater than 1. So in that case, somehow we have the C here is unbounded on one side. So lambda times C still in C, so C is unbounded on some direction, on all the on some direction. So in this case, for this kind of set C, then we can have the domain of the negative root C is the horizon cone of C. Then we also have this two result here. So the root C is continuous at those points here relative to this horizon cone of C. So we're talking about the Lucy is continuous at the single point, all this point here. Then the second conclusion here is Lucy is continuous relative to the horizon cone if and only if this near end of C is closed, plus this condition is true. All right. So that is somehow we say the near end of the horizon cone, the near end of horizon cone, that means you have some part of the, you're looking at the kind of a cone. If you're looking at the cone here, then if you suddenly have a x0 is somewhere below the cone, then in that case, you have the near end is kind of all the faces. Then that's you have this horizon direction, but this one cannot intersect the poles of C here. So they have, or they just intersect at the 0 points. All right, so this is about the continuity of the horizon cone, the gauge function and the cogauge function. So that's the continuity. So again, here we say, what's the importance of the far end, near end here? So we can apply this one to talk about the continuity of the some other functions which are interested in the convex analysis. Then the third part, I'll talk about local error bound modulus. So this is in regarding to the calculation about the some parameter in this stability system. So it is always important to say how can we identify, how can we calculate or present analytic formula. Of course, probably you can have some numerical procedure to calculate those modulus, but it is always in our interest if we can give an analytic formula or the information you are required of this one kind of doable, so you can have finite information to calculate this modulus. Right? So this modulus is always important in variational analysis. So here I'll talk about the how do we calculate all this local error bound modulus. So for a function f, which is no semi-continuous, then we have a point x bar, so which is in this level set. F is less than or equal to 0. Then first we have the when this function has local error bounds at x bar. So in that case, if we have a positive tau, then we have a positive epsilon such that this tau times this distance from x to the level set, which is less than or equal to this residual f of x, where for all the x which is in an epsilon neighborhood of x bar. So we're looking for this kind of tau number here, parameter here. So this tau needs to be positive, can be any number. So epsilon here can be any positive number, but tau here, as you can see here, if one tau satisfies this inequality, then any smaller tau also satisfies this inequality. So the local error bound modular is looking for the largest tau, which is satisfy this inequality for neighborhood of x bar. Right. So this is basically the definition of the local error bound modulus. So what is it? Because any tau probably not the beta, but the largest tau for this inequality, which might provide some useful information. So that's the local error bound modulus. By definition, this parameter can also be defined as this limit if when x tends to x bar, and we have this f of x is positive of this quotient here. f over the distance, or just move this inequality around. But one very important information here is that the f of x, this function value, when you take the limit, so this function value must be positive. Right. So this one is very important information for this one here. So we have this, we can represent the error bound modulus by this formula here. But as we can say, as we know from the calculus, calculating this limit is very difficult, even in 2 dimensions. Right. So directly to use this limit if to calculate this local error bound, basically we say this is not attractive. So what we want to do here, if it is possible, we can represent this local error bound, this modulus, by some other information, known information, probably at only 1 point x bar or something else. But in case we cannot compute this local error bound exactly, then probably we could get a lower bound or we could get an upper bound. Right. Then first we say x bar is in the level set, but if x bar is in the interior of this level set, then we can say that the local error bound modulus is always plus infinity. So any tau is okay. So in that case, it's not of much interest. So we assume the x bar, it is at the boundary point of this level set in all the following results. Right. So this another very important concept to present the local error bound modulus. So it's called the outer limiting subdifferential of outer limiting subdifferential. So basically it is kind of outer limits of the subdifferential. Basically it is limiting subdifferential. Right. But we say this outer limiting subdifferential is the limit of the VC where the VC is in the subdifferential of f at xk. Then when xk here tends to x bar attentive to f, that means you have a sequence tends to x bar, and also its function value f of xk also tends to f of x bar. Very important here, we also require that the function value f of xk is greater than f of x bar. So that's, I think, why the research introduced this concept here. Outer, so outer meaning we have from the outside of the level set. Right? Because basically, if you have the, I remember in the definition of the modulus, then this under this limit soup, we have the f of x must be positive. Right. So in that way, so we can have this one here. Of course, here now this one basically is now equal to 0. So this is a very important concept for present one of the local error bound modulus. So immediately, so with this concept, one of the lower bound for this lower bound local error bound modulus is presented as the distance from 0 to this outer limited subdifferential. So immediately this distance gives us local error bound modulus. All right. So what's important here is this, as we say, if this distance is positive, then this local error bound is positive. This amounts to the function itself has the local error bound at x bar. Right. In addition, if you have a function f is convex lower semi-continuous, then we can have this originally is a lower bound. As long as the function f is convex, then this lower bound becomes tight. basically which equals to the error bound, local error bound modulus. All right. So this, I think, this few slides here is the start of the research on the local error bound modulus. All right. I represent this one here, outer limited subdifferential and the lower bound, and if F is convex. All right. So those 9 of research have been presented in the paper by Alex and the N and the Michelle or something, and by Fabian in 2010, and also by Yofei, Alex Yofei in 2015. Right. So that's the they have a starting from a lower bound. Then on the other count here about the sublinear case. So in this case, say if we now have a function f, which is sublinear. So in this case, sublinear is have a very good structure. So we have a f here is a sublinear and a no semi-continuous. So in this case, Hu and Wang in 2011, they proved that this local error bound modulus is exactly equal to the distance from 0 to the far end of C relative to 0. All right. So what is this C? So C here is the unique closed convex set such that the f function is equal to the support of the C. So if f is a sublinear function, then there is a unique closed convex set such that f basically is a support function. All right. So this is how this C comes from. So in this case, f is sublinear, then we can have error bound modulus is equal to this distance from 0 to the far end. Right. So that's the one result by Hu and Wang. So in this case, if we use what we had before to present the geometric structure about the far end. So remember, we have the far end of a convex set is in between one of the union and the closure of this union. So in that way here, again, for this convex set C, now it lies between the union of the exposed face of the C. On the other side is the closure of the exposed face of C. All right. So we also have this far end is included in this outer limit subdifferential of the support function at 0. So with this inclusion and also the inequality, because with this one here, now we can write down the local error bound modulus is also equal to the distance from 0 to the outer limited subdifferential of this. Of course, this is this one here, right? So for the sublinear function. And the same way, because f now is just the support function, so this distance can also be written as the distance from 0 to this outer limit subdifferential, because f basically is the same as the support function. So this is the case, the error bound modulus is equal to the distance, this distance here, where the C is this that unique convex set for the sublinear function. So when we read this paper, we started to wondering, so we have this one here. So if we replace this C, so this C is coming from the sublinear function. But if we do not, if the function is not sublinear, but we have something else, we have the subdifferential of the function. So our basically starting point here is if we replace this C by the subdifferential of some functions we are interested, then what we can do? So in this case, basically we get this upper bound result. So suppose f here is locally Lipschitz and regular function. So in that case, if, as we can say here, if we just replace the early result for the sublinear function, that is C by the subdifferential of the f function, then we can get this distance here is the upper bound for the error bound modulus. So in this case, in general, we only say the f is locally Lipschitz and regular. So this is more general than convex and than the sublinear function. Right. So in that case, in this originally in the literature, there is this local this lower bound. Now we can have an upper bound for this local error bound modulus. Right. But since we still do not have this tight bound, still a lower bound or still upper bound. So even though I say the thing is that this upper bound or the lower bound, we say in our view is computable. When we argue, when we're writing up the research proposal, ground proposal, so we say this is good, this is computable, right? So in that case, we say this is better than the original definition of that limit soup of this local error bound modulus. We say this is kind of computable upper bound for what we want, we are interested. So the same reason that this distance is equal to the distance from 0 to the far end of this subdifferential here. All right. So now we get the upper bound. Now we want when this upper bound possibly comes to be tight. All right. So we are going to study this lower C1 function. So lower C1 is defined as the maximum of a two variable function phi of x and y over the parameter y is in this indexed y. So indexed the y here, this indexed we assume it is compact, and also we assume this phi function when y is fixed is C1 function in variable x. Right. Of course, there are other conditions for the definition of the lower C1. So I just briefly present this one here. Then what we can do for this one here. So this one basically is kind of the maximum of some function here. So this is some kind of upper envelope of this class of the phi function. So if it's upper envelope, so this f function possibly locally at x bar has some convex structure because the maximum of something. So it doesn't matter. Of course, phi function is C1. So we are looking at this maximum of C1 function. So locally, we may have some kind of convexity property there. So in that case, we are saying if for this lower C1, even though it is not convex, whether this lower bound can become tight. Right. So this one is indeed true. Before that, I briefly introduced some notation here. So the first one here is the active indexes of y of x. All right. So as long as you have this phi attains its maximum, so we have this all the y, small y, so that's the active indexed mapping. Now I have another two notation here for the indexed is the limit of the active indexed when xk tends to x bar, and also we require the f of xk is positive. All right. So I call this one here is outer limiting active indexed. Then the second one here is the script y outer of x bar. So this one is the optimal solution set of this optimization problem. With that requirement here, this optimal value is positive. Right? So for this one here, as now you have existence of the W, so we're starting from x bar. So as if you have an existence of the W bar, W, such that this optimization problem have a positive optimization, optimal optimal value, then this argmax is put in this index set. Right? So with these two index sets, now we can present it. Indeed, we have a tight lower bound. So in this case, we have f function is lower C1. So then if it's lower C1, now I have the distance function. This lower bound, originally it is a lower bound. It is indeed tight to be the local error bound modulus. Moreover, we can write down this outer limited subdifferential explicitly as the union of this convex hole of this active index set of this gradient for all this y in the active index set. That's that particular index set. And also we can have this far end of the subdifferential, which is bounded by this union and its closure. All right, so that's in this case we can have this result here. Then we come to say on another end we have an upper bound by using the subdifferential of the support of the subdifferential can present us with the upper bound. Now one question here, that bound, upper bound, you assume the locally Lipschitz function, right? But our question says that if it is come back to the convex function, because convex function give a lower bound which is tight, but it comes to if the for the convex function, if your upper bound is good or not. All right, so this way we say it is we can have a tight upper bound for the convex function. So we assume here f is finite and convex on some convex neighborhood of x bar. Right. Two assumption here we need is if the Aberdeen constraint qualification holds, so basically it says that the set of the critical directions is equal to the tangent tangent cone of the level set at this point. Right. So in that case, so basically, says this is the Aberdeen constraint qualification. Right. Then the second condition we say the level set admits exact tangent approximation. So this means that we have a neighborhood of x bar. In this neighborhood, this level set basically is identical to its tangent cone. So in that case, we say the level set admits the exact tangent approximation, because in that case, we have a neighborhood, the level set basically is equal to the tangent. So this one basically I mentioned early in the work with Kaiwa and Vera, we used this one to study the some other property in the convex analysis. So for the convex function with this two additional assumption, indeed we can prove that this upper bound, which is originally upper bound, now becomes tight, is equal to the local error bound modulus. All right. Then I have one final result here. So in this case, now we come to consider the linear semi-infinite system. Right. Now we have this inequality here. AY inner product with X is less than or equal to B. Now we have this index set Y is a complex space. Right. Now we assume that the AY and the BY here depends continuously on this parameter Y. Now in that case, now we can define that the F here is the maximum of all these affine linear function, And also this active index set is all the y such that this affine attains its maximum. So that's the active index set. We, to present our results, we need the concept that our system, linear semi-infinite system, so this one is called a linear semi-infinite system, is locally polyhedral. If this one is true, so that's this polar for the poles and convex hull of all this AY for the active index set. So this one is equal to the poles of this level set minus X. So that's the so-called locally polyhedral. So we also in our work with Kelvin and Vera, we use this concept. Right? So that's something which probably not globally polyhedral, but locally you can use this one here. So in this way, we can now present for this linear semi-infinite system. Now we can say one of these two results, one of these two conditions is satisfied. And also we can say these two conditions here themselves are equivalent. So A here is that originally that exact tangent approximation holds at X bar. Then the second condition here is the linear semi-infinite system is locally polyhedral. So under one of these conditions, indeed, now we can write down a kind of formula for the local error bound modulus. So which is the distance from 0 to this union of the convex hull of the AY, where Y is in that Y prime. So what is the Y prime? So Y prime is one of the elements in this set. So this is a particular set different from before. So this set here is defined by this one here. So what it is here, so now we have Y prime. So this Y prime is a subset of the active index set. So if there exists a W such that for all the Y in Y prime, this inner product is equal to 1. If Y is not in Y prime, then this inner product is less than 1, strictly less 1. Right? So we define this one, so that is a script Y. So now we can write down this local error bound modulus as the distance from 0 to this union. So this we have the concert, this linear semi-infinite system. All right, so this basically, this result extend the early results for finite linear system, right? Because the finite linear system, the affine system, so basically it's always locally polyhedral, right? So by Canovas, by Marco, they presented this result in 2014 for this finite linear system, right? So we have all this constructor are the same, right? So only difference here now we have a semi-infinite system, right? That's basically what I'm going to present. To conclude, I might mention 2 points. Basically, I have mentioned many times. All right. So one point here is that this far end of the subdifferential, in particular, the distance from 0 to this far end set is positive, plays an important role of regularity assumption. All right. So this case here, so normally sometimes if you have a nice polyhedral system, then that's a very good structure in the variational analysis. But sometimes if you come back to a convex set, then something probably does not work. All right, so line between the polyhedral system or a convex system, in this in between, I think this far end set might play some role for us to do something. Then again, the second point just say that to my knowledge, the modulus of the weak sharp minima has been used in the convergence analysis for some optimal algorithms. So we think that the upper bound of the local error bound modulus or the lower bound modulus or the local error bound modulus itself will also play some similar, oh, the last word is a typo, similar role in the analysis of the optimal algorithms. Right? But we're still working on this one, possibly. All right. So that's the conclusion I want to give here. All right. So that's the end of my talk.
Thank you very much for your talk. So we have one comment from Marco in the chat. So can you read the chat?
Me?
Yeah. So
Marco, we don't hear you.
Marco, unmute your phone.
And now? Now?
Yeah.
Good now.
Okay.
Yes.
A little observation. The first part is you quoted a paper by Anderson and Goberna. Actually, it's Anderson, Goberna, and Lopez, but it's not important, no? And the one in which we introduce these concepts of locally polyhedral sets, no?
Yeah,
and
yeah.
the second is just, I claim that after this kind of talks, I fall in love with convex analysis even more than I was in the past. Okay, congratulations, and okay, good night or good morning. Up to you.
Thank you, Mark. Yeah, it's very nice to see you here. Yeah.
Okay, yes, the same.
May I ask a short question? First of all, I share the remark by Marco. Now I indeed love convex analysis more. Thank you, Xiaoqi. My question relates to your second comment in the conclusions. So indeed, it's been a lot of research on error bounds, and normally people are looking for lower estimates, lower bounds for the modulus, which ensure error bounds, sufficient conditions. Of course, they are also used in convergence analysis and many, many other things. Not much research is about the upper bounds. Probably, Xiaoqi, you and your courses are the only group who develops that. I might be wrong, I don't know. You write here that you anticipate that the upper bound will play a similar role in convergence analysis. What makes you anticipate any role of the upper bound? Because they don't guarantee the error bounds. Probably they're not enough to guarantee good properties of algorithms. It's not criticism, just a question.
Yeah, we say that the upper bound here. So basically, we say, yeah, this way. I mean, my research in the this error bound area is just on the starting point. The literature, I think, is huge about the last 30 or 40 years since the last century 80s. There's huge amount of the research, the literature about even the error bound itself. There are many, many papers, or not even other weak sharp minima, other things. I'm new here, but we just come into this point to do that, to replace that CTC for the sublinear function by the subdifferential of a local Lipschitz function. Now we come up to the upper bound. So why this upper bound? Just says that, yeah, lower bound is used for, I say, you mentioned as a sufficient condition. Upper bound, I don't have a concrete reply here. So I just, so possibly, if we do not know the exact bound exactly, so the upper bound might be useful. I'm saying it might be useful. I do not say it is useful. Because this research, this paper, I think is only my first paper or my second paper on the error bounds. Thank you, Alex.
So let your anticipations come true. Thank you, Xiaoqi.
Is there any other questions from the audience? So I think thank you very much for again the speaker for your talk. So I think if there,
thank you.
Yeah.
Thank you for your coming. Yeah. Bye bye. Bye bye.
Yeah.
Thank
so,
you, Xiaoqi.
Thank you, Xiaoqi.
Yeah. Hope you see you soon.
Hope to see you.
Yes, we hope to see you soon, indeed.
Yeah. Yeah.
Thank you, Xiaoqi. Thank you. Great talk.
Hope we can travel somewhere. Okay. Bye bye.
Why somewhere? Why not in Hong Kong?